Hello, today, once again, we're going to be going over a problem from HackerRank. Today we'll be doing the binary search tree lowest common ancestor problem. I have not seen this problem before, but it does say the difficulty is easy and only has an 89% success rate. So let's begin. You are given pointer to the root of the binary search tree in two values v1 and v2. Just making sure that the solution can be submitted in Java. You need to return the lowest common ancestor LCA of v1 and v2. Lowest common ancestor in the binary search tree. You only need to complete the function. Okay, I'm giving the function pointer to a root node, lowest common ancestor, and I should return a pointer to that node here, right? Return the lowest common ancestor. Okay. Integer 1 and 2. It is guaranteed that variable 1 you're given pointer to the lowest common ancestor of two nodes. Okay. And it's guaranteed that v1 and v2 are present in the tree. So if v1 and v2 is 7, the lowest common ancestor is 4, right? Yes, because the ancestor of 1 is 2, the direct parent, and then 1 is a child of 2, 2 is also a child of 4, which is also a parent of 7. Okay. So how do we solve this problem? What we need to do is find where let's think about it. A common ancestor, huh? We could print the path to both 1 and 7 using a binary search tree. So that's 2 times log of n as far as searching goes, and then we do a simple string comparison, which is at most we're comparing log of n entries. So that's 3 log of n. Yeah, 1 search, 2 search, and a 3rd search. Okay, I think that's actually a good solution. So search for 1, search for variable 1, search for variable 2. Oh, and you have to note the path as well. So that's what you have to do. And then and there's a path because v1 and v2 are guaranteed to be in the tree. Okay. So with that assumption, yeah, the keynote here is that v1, v2 exist in tree. Okay, no problem. So algorithm, find v1, find path to v1, find path to v2, compare paths. Yes, compare paths until we find ancestor. I guess a fringe case is if well, they're both the root v1 v2. It's the same one. Yeah, it's the same thing. Yeah. So just for example, the path to 7 is left, right, and the path to 4 is left, right. Then we need to find this path here. So we have path 1, find path P1 to path P2. So this is P1, this is P2. Now 0 is going to indicate a left movement, and then 1 is going to indicate a right movement. So looking at just looking at this tree, that's the example. The path to 7 would be 1. The path to 4 or 1 would be 0, 0. Hold on. Oh wait, so this is gonna, they all start out root obviously, or no. So if the first and second character are different, then so P1 at 0 not equal to P2 at 0, and then you have the LCA is equal to root. And if you have, let's now use the examples 1 and 3. Let's get some water real quick. We have LCA, find the lowest common ancestor, P1 and P2. Now we're going to use the example 1 and 3. So the path to 1 is 0, 0, and the path to 3 is 0, 3. And so now we can for sure say, or 0, 1 rather. That's left, left, and right, right. So we can say that when it's different, when the path, when the if P1 dot length greater than P2. Well, I need to see one more example just to be sure. Say 3, or say this was 5, and this was, there was one more entry down here to the right. Here. Alright, so 5 would be, or to 4 it would be, there we go, like that. So to get to 4 you would get 0, or yeah, 0, 1, 1. When you get to 1 you would get 0, 0. And then you can see that this part matches all the way up to this part. So the path to true is 2. Right? Yeah, there we go. So how do we find it? Oh, easy. So this is length 3 and 2, so you iterate 1 time. Because if this was, say, let's say for some reason we just have to do more of these. Right. So the path to 4 would be, we're gonna have to find an index at which find the index at which they differ. So we're gonna have to have a comparator. I'm not really liking the solution anymore, to be honest. Oh, here, that's right. You don't I messed up. You don't find the path. You find the values in the order that you found them. You find the values, and then you search the values until you find the matching one. The values. Okay, so I guess you can call that the path. So, but the path is just the numbers to v1 and v2. So, like for example, the path to 7 is just 5, right? Or ancestors. I guess you can call a list of ancestors. And then path to 1 is 5, 2. So we begin to look until we find. So, like for example, these could be way over here, right? And then we just search we look at 5, and then if we had another one here, right, we would just keep going until we find a no match, and we can go to the parent. So I'm just gonna create a well, I don't know the maximum depth of the tree. Oh right, so what was I? Oh yeah, I need to go to the algorithm. Find path 1 P2, compare ancestors and path. Oh, so it's like what we call ancestry. There you go, that's a good word. Find ancestry A1, A2 to V1, V2, right? And then we don't need this. It doesn't make any sense. This is ancestry of 5 to 1, or 7 and 1. Okay. Yep. So I'll go find compare ancestors. Yeah, compare ancestors and path. So different, then return the last ancestor. And when they say lowest, they mean lowest in the tree, not lowest, not ancestor, lowest value. This would need to be a clarification. Okay, so so we need two arrays of nodes, actually. Node array E and ancestor 1 is equal to new node array, and I'll just say 100. I could find the depth of the tree, you know, the counter, but we don't need to do that. I would just clarify this with the interviewer, see what the maximum depth is. It's not that I'll just write the find deep depth of tree function. It wouldn't matter. Now that I think about it, a tree would make a great architecture if you were dealing with objects or databases larger or multiple servers large, where each data object might be greater than the size of the server itself. So we need two of these actually. And now we gotta search for the tree. So get past one. Well, I guess we can make a method for getting the path to A1 and A2, so we don't have to repeat ourselves. Or we can repeat ourselves. Anyway, and V1 and V2 are guaranteed to be in the string. So I'll just create a new node A1 here. A for ancestry. So now we just go through the looking for V1. So while root.data is not equal to put something in the root. Yeah, whatever. What we'll do is we'll just set it to null. So now where a1 a at I is going to be equal to root.data. Let's run that code, make sure it compiles real quick. What? I think the sample, this will happen to be 6. that's not the that's not the solution. Now you have to compare them. A1 A1 is equal to, that's about it really. Wait, no, that's right. Yeah, 1.1 of them is going to hit null. If not, then it's just the last parent. Temp is going to be equal to A1. If A1 is equal to temp is going to be equal to A1 at I. And then we examine the next letter. Else we return. We break actually. And return ancestor. And I don't think we have this check anymore because there you go. It's awesome. Skip that. We'll see in a second here. What's that? 195. Else. Oh, yeah. Whoops. But there we go. What the fuck? Oops. Incorrect. Oh, what happened? That was incorrect. Damn, I hate this. I always go full in betting on a solution, then not debug it. I'm just debugging the problem. There we go. Forgot to increment the I down here. Damn. Alright, and there you go. That's the solution.